All right. As you know, guys, chapter 2 is about matrices. And last time we did a few questions from exercise 3.1. It was about matrix operations. When we say operation, we mean mathematical operations, right? Adding two things and subtracting, or division or multiplication, and also raising to the power, right? So next one is matrix algebra. And when we just say algebra, right, the first thing that comes to our mind is variable, right? That x, y, z, because algebra is a kind of tool, and that actually, how to say, using this tool, we solve mathematical problems. Of course, we have some different methods, but algebra is very powerful tool to solve algebraic, I mean, the mathematical problems. And the method of using algebra, usually if you are dealing with a problem, we have to introduce some variables, right, to denote the unknowns in the problem. And after that, we will find out how these variables are connected to each other. That means that we need to form the equation. Then after that, by solving the equation, we will try to find the solution to the problem. And that is what algebra means. Okay, so in this chapter, the matrix algebra, what we have here, let me just have a look quickly what we have here, and after that we'll continue from here. In 2.2, 3.2, okay, matrix algebra, we have, let me just share it here. Okay. All right, the second one, matrix algebra, algebraic properties of matrix addition and scalar multiplication. And these are really easy. It's very similar to the properties of real numbers, right? A plus B equals B plus A, and blah, blah, blah. And some examples. Okay, and the linear combination of matrices is also very similar to linear combination of vectors. And also definition is exactly the same, but instead of vectors, here we have matrices. And okay, properties of matrix multiplication. And also that's an important property. Actually, A times B is not equal to B times A. That is shown in the video with this example. And also A means is defined as A squared, or A squared is defined as A times A. And the properties of matrix multiplication. The first one is associativity, that is A times BC equals AB times C. That means that if you are given three matrices and we need to multiply these matrices together from the left, A and B and C in that order. If you multiply first B by C and after that multiply A by the result, it's the same as first multiply A by B and after that multiply the result by C. And also here we have A times B plus C. It's very similar to real numbers, so I think it's not so hard to understand these properties. And one thing is the proof why the second property, I mean the first property, A times BC equals AB times C. It's given by using this sigma notation. And okay, these are the examples. And these are important properties of the transpose. A transpose equals A, and A plus B transpose, especially T. I mean, you should be very familiar or comfortable with this property. AB transpose is equal to B transpose A transpose. And also proof is given in the video. Those are the things. And also about square matrix. If A is a square matrix, then A plus A transpose is a symmetric matrix. And for any matrix A transpose, and A transpose A are symmetric matrices. These are the things in 3.2. So we are going to talk about this stuff. I mean, solve problems related to this stuff. Okay. All right. Let's say a few questions, and after that, maybe 20 minutes, have some break, and 20 minutes, I'll finish the plus. So let's start with exercise 3.2. I asked Yihin to solve odd numbered questions. So here, I'll try to solve only a few even numbered questions. Okay. So in exercises 1 to 4, solve the equation for x. Given that matrix A equals this, matrix B equals this, and that's quite easy thing, so I will skip this. For example, question 4. It's like algebra, right? Here, question 4, you should just remove the brackets, take unknowns to the left-hand side, and what is it? Constant matrices to the right-hand side, and just solve this. It's like 2a minus 2b plus 2x is equal to 2x minus 3a. Now, if you take this one is 3x. Take everything to the left-hand side. Here we have 2x minus 3x. Here we have minus x. And the 2a minus 3a minus 2a, that is minus 5a on the right-hand side. Negative 2b, take to the right-hand side, it is plus 2b. Now, if you multiply both sides by negative 1, we know how to multiply a matrix by a scalar, right? Just we need to multiply every component by negative 1. So that is x will be equal to 5a minus 2b, right? And what is 5a? 5a is, we need to multiply each component of matrix A by 5, 5, 10, 15, 20. So here we have 5, 10, 5 times 3, 15, 5 times 4, it is 20. Minus 2 times B, it is 2 times negative 1, it is negative 2, it is 0, 2, 2. And just subtract the corresponding components, right, or entries. 5 minus minus 2, it is 7, 10 minus 0, it is 10, 15 minus 2, it is 13, 20 minus 2, it is 18. That is one example solving kind of equations, very similar to solving equations in algebra. But if you have multiplication at that time, you should be a little bit careful. In exercises 5 to 8, write B as a linear combination of the other matrices, if possible. Okay, if possible, that means that it may not be possible, it may be possible. Okay, how to do that? And here the method is similar. Actually, for 8 is a bit long, that's why let's just do question 6 here, for example. Okay, but the idea is the same. So that means what is asked here? Question 6. Okay, it says write B as a linear combination of the other matrices, if possible. And in question 6, here we are given matrix B. It is a 2 by 2 matrix, right? And here we have 1, 2, 3 matrices. So that means that we are looking for some numbers where that B is equal to, let's say, is equal to x times capital A1 plus y times capital A2 plus z xyz times capital A3. Capital A3. That is what we are looking for. Now, what is x times capital A1? So actually, do such numbers exist or not? We are looking for this. Now you will see that actually it is again like solving the system of equations, because to answer this question, now we'll end up with a system of equations. And after that, we know how to solve system of linear equations and answer this question. So x times A1. So here we have 1. 1 is identity matrix. So here we have x 0, 0, x plus y times A2. So here we have 0 and negative 1 times y, negative y, and 1 times y, it is y, and here we have 0. Plus multiply A3 by z. So here we have z, z, 0, z. And on the right hand side, here we have b. That is 2, 3, negative 4, and 2. Right? Now, on the left hand side, we have 3 matrices of the same order, right? We can add them. If you add this, what we have here? Here we have x plus 0 plus z is equal to 2. So here we have x plus z is equal to 2. And the second component, 0 plus negative 2 plus z equals 3. That is negative y plus z is equal to 3. And the third component, 0 plus y plus 0 equals negative 4. So that means y equals negative 4. And the last component, y plus 0 plus z equals 2. So here we have y plus z equals 2, right? So immediately here, just we need to answer the question. We can form your system of linear equations, or from here, since y equals -4, if I substitute into this equation, what we got here? From here, we get z equals 2 plus 4, that's equal to 6. And if you substitute here, for example, what is y? It is -4. -4 plus, what is z? Z equals 6 plus 6. On the right hand side, it is 3. So t equals 3. Here we have contradiction. That means that actually it's not possible to write b as a linear combination of a1, a2, a3. Okay, that's just a short way, because so clear, I mean, obvious here, right, to write the answer. So even I don't have to form the system of linear equations. Okay, if it is like a big one at the time, you better form the system of linear equations and write it in augmented matrix form. And after that, you reduce this to reduced row echelon form and get the answer. Okay. In exercises 9 and 9 to 12, find the general form of the span of the indicated matrices, as in example 3.17. Okay, span of A1, A2, A3, right? So the span of A1, A2, A3, what is it? Actually, these are all the linear combinations of these matrices, right? So we are talking about, let's say what we did here, we did question 3, right? And it's talking, we are talking about these three matrices. Again, if we just do these three matrices, the first one is 1 0 0 1. So here our a1 is, we're talking about question 6, a1 is, actually I didn't matrix, 1 0 0 1, and a2 is, what is it, 0 minus 1, 0 minus 1 1 0. And A3, what is A3? A3 is 1110. So that is 1110. Is it like this? Oh, it's like this. So 0, 1. Okay. So you're talking about all the possible linear combinations of these matrices, right? What are these? Actually, these are these numbers: A, capital A1, plus B, capital A2, plus C, capital A3. And we have already obtained this. Actually, what is this? Here we have, we just write here, that is, the first one is x plus z, right? So that is a plus 0 plus c. So here we have a plus c. And the second component, 0, I mean b 0 and minus b plus c. So here we have minus b plus c. Third component, here we have 0 plus 1 plus 0. That's just b. So here we have b. The last component, 1, it is b, and 0 c. So here we have b plus c, right? So that's what we have here. Okay. So from here, a plus c, and here we have b minus b plus c and b plus c, right? And what do we see here? That means that all the matrices,
Hello,
right?
sir.
Yes.
Not B plus C, A plus C, sir.
The last one?
Yes, sir.
That's correct, right? Okay. Thank you very much, Simei. So here we have a plus c minus b plus c, and here we have b, right? So that means that all the matrices, if you're talking about here, okay, here let's say it is M2 and by 2. These are, actually, this is a set that contains all 2 by 2 matrices. Okay, so what is the span of these three matrices? It gives us some kind of set here. Okay, let me just write here S. Let me just not write use S here. It is S whose components satisfy this properties. Okay, if you're given any four numbers, this A, B, C are any real numbers, right? This A, B, and C are any real numbers. Okay, if you just take any matrix from here, if they satisfy this equation, like A plus C and A plus C, that means that these numbers in the main diagonal, they are equal. And here we have minus B plus C and B. Okay, all matrices like which satisfy this condition are in this set. That is the span of these matrices. Okay, so it's the set which is filled by matrices which is in this form. All right, another example, determine whether the given matrices are linearly independent. Well, let's do this question quickly, maybe one example, and after that we'll have break because we have 4 minutes left. And we have, I know you have class at 11 o'clock. Okay, so we will have 30 more minutes and finish the class. Anyway, so it says determine whether the given matrices are linearly independent. To be linearly independent, right, if you're talking about, let's do question 14. All right, the only way that if I multiply the first matrix by A, let's say it is, or maybe X, let's say X, the first one is 1, 2, 4, 3, 1, 2, 4, 3, plus Y, it is 2, 1, 2, 1, negative 1, 0, negative 1, 0, plus Z, the last one is 1, 1, 1, 1. Okay, so do we have any non-zero, at least one of these numbers? We are talking about this X and Y and Z. These are real numbers. And can we find such numbers where X times the first matrix, Y times the second one, and Z times the third one is equal to 0 matrix? Can we just find three numbers, at least one of them is not equal to 0, so that is equal to, I mean, their linear combination is equal to 0 matrix? If it is so, we know that that means these matrices are linearly dependent. Otherwise, if the only way to write this matrix is 0 when X equals 0, Y equals 0, Z equals 0, that means that these matrices are linearly independent. Again, guys, when we talk about subspace and bases, at that time you'll have more idea what we mean by linear independence and linear dependence. Okay, at the time these concepts are really important. So to answer this question again, as you see here, we get this system of equations, right? If you just multiply the first matrix by X, the second one by Y, the third one by Z, and after that, if you just add these three matrices together, and the first component should be equal to 0, the second component should be equal to 0, because we know that two matrices are equal if and only if they have the same sizes and their corresponding entries are equal. So from the first one, X times 1, so here we have X, 2 times Y, here we have 2Y, and Z times 1, so it is Z is equal to 0. And the second component, 2 times X, here we have 2X, Y times 1 plus Y, and plus Z is equal to 0. Third one, 4X minus Y and plus Z is equal to 0. The last one, 3X, Y is 0, and plus Y is equal to 0. Okay. Now, if you just solve this by Gauss-Jordan elimination method, if I just form our augmented matrix, the first one is 1, 2, 1, right? And the last one is 0. The second one, it is 2, 1, 1. Third one is 4, negative 1, 1. The last one is 3, 0, 1. Actually, the last one is 0, 0. Actually, we just know that we have a 0 column here. Okay. Usually, if you actually know that we have 0 column, you don't have to write this to save time. Okay. Now we have to reduce this to reduced to echelon form. And okay. So how can we do this? Guys, let me just stop here. Okay, because now it's going to turn off soon. We have less than 1 minute left. Let's have some break, and from here we will continue, or maybe you will finish it yourself, and or maybe I just write the answer and continue with the next example. Okay, let's have a break for 10 minutes. After 10 minutes, we will continue our class.